You know that feeling. You're staring at a challenging problem, maybe grappling with a complex algorithm, and it feels less like a puzzle to be solved and more like a tangled knot of possibilities. You know there's an optimal way through, but tracing the right steps, figuring out where to even begin, it feels overwhelming. If that resonates, well, you're in the right place. Today, we're taking a really deep dive into dynamic programming, a powerful technique built specifically for untangling those kinds of problems. We're not just talking about what DP is, but walking step by step through how you actually approach solving a problem using this method. Our goal is to provide a framework that helps these concepts truly click, making complex problems feel not just solvable, but understandable enough that the solutions, they stick with you long after this conversation.
And to guide us through this, we're drawing primarily from the Hello Algo resource, specifically section 14.3, which lays out a really practical step-by-step approach to tackling dynamic programming problems. It's quite good. Just to quickly anchor us, because we've touched on this before, dynamic programming problems typically share three core characteristics. They have overlapping subproblems, meaning the same smaller problem needs to be solved multiple times within the larger one. They exhibit optimal substructure, where the optimal solution to the overall problem is composed of the optimal solutions to its subproblems. And they have no after effects, basically. Decisions you make early on don't invalidate later decisions. You only need to know the state you reached, not how you got there.
Right, and those are the classic definitions. But, the source points out something important. Spotting those traits directly in a complex problem description can be really, really hard sometimes. So before we even get to solving, how do you realistically determine if dynamic programming is the right tool for a given problem? What's the practical first step?
That's exactly it. Instead of immediately trying to, say, prove optimal substructure or find overlapping subproblems, which can be tough, the most effective starting point is often to see if the problem fits a decision tree model. Can you think of the process of solving the problem as making a sequence of explicit choices?
A decision tree, like picturing yourself at crossroads, making a choice at each step. If I have to pick item A or B, then from there pick C or D, kind of mapping out all those possibilities.
Precisely. If the problem solution involves a sequence of decisions like that, it naturally lends itself to exploration via a tree-like structure. Problems that fit this model are usually solvable, at least initially, with simpler approaches like backtracking or exhaustive search, which explore all possible decision sequences.
Okay, so if I can kind of draw a diagram of choices and paths to a solution, that's the first big hint. That makes sense.
Exactly. That decision structure is the primary indicator. And then the source gives us these bonus points that, when combined with the decision tree model, heavily favor dynamic programming.
Bonus points. Okay, I like the sound of that. What are those? What else should we look for?
Well, the biggest one is if the problem's objective is to find an optimal value, things like finding the minimum cost, the maximum profit, the longest possible sequence, the fewest operations, if you're trying to maximize or minimize something, that's a really strong signal.
An optimization goal. Okay, got it.
Yes. And another key bonus point is if the problem state can be represented neatly, often using simple data structures like maybe a list or a multidimensional matrix, and crucially, if there's a clear, discernible recursive relationship between a state and its preceding or neighboring states, like how the solution for a state, say ij, depends on states like I1j or ij1.
So I'm looking for a sequence of decisions, an optimization goal, and a structure where the solution for one step clearly depends on the solutions for previous steps, solutions that I could maybe store in a table.
You got it. That's the trifecta, really. And conversely, the source mentions penalty points where DP might be less suitable. For instance, if the goal is to find all possible solutions, not just one optimal one, or if the problem involves finding specific permutations or combinations where the path itself matters and can't just be summarized by a single state value, you might lean away from standard DP.
That makes sense. DP is usually about finding the best value, right? Not necessarily reconstructing every way to get there or finding all the different variations.
Exactly.
Yeah.
So the practical rule of thumb from the source is, if it fits the decision tree model and has those strong optimization or state dependency signals, tentatively assume it's a DP problem and proceed with the solving steps. Trying to apply the steps will often confirm or deny your assumption pretty quickly.
Right. Tentative diagnosis, DP problem. Okay. Now, for the core of it, the actual process of solving, the source lays out a clear sequence of steps. What's the game plan?
Right. The general blueprint involves a few key things. First, articulating the decisions you make at each point. Second, formally defining the state of the problem, what information captures the essence of a subproblem. Third, conceptualizing or establishing a DP table to store results. Fourth, deriving the state transition equation that links states. And finally, figuring out the boundary conditions, the starting points.
That list, okay, it sounds logical, but it still feels a bit abstract. Can we make it really concrete? Maybe walk us through an example using these steps.
Absolutely. The source uses a very common, I think, intuitive example to illustrate these steps. The minimum path sum problem on a grid.
Ah, yes, the grid traversal one. I think many listeners will have encountered variations of this in coding challenges or interviews. Tell us about the specific problem.
Okay, so the problem is this. You're given an n times m grid, and each cell in the grid contains a cost, just a number. You start at the top left corner, cell 0. At any cell, you can only move either down or right. The goal is to find a path from the top left, 0, 0, to the bottom right corner, n1, m1, such that the sum of the costs along that path is minimized. The source shows a simple example grid where the minimum path sum turns out to be 13.
Okay, simple rules, clear objective, minimize the total cost to get from start to end, only moving down or right. Let's apply the steps you mentioned. Step 1, decisions, state, and DP table.
So what's the decision at any cell ij in the grid? What choices do you have?
Well, if I'm at ij, my only options are to move down to I plus 1j, assuming I'm not at the bottom row,
Right.
or move right to ij plus 1, assuming I'm not at the rightmost column.
Simple decisions. Good.
But
Now, what information do you need to capture to define a state that represents a subproblem? What defines where you are in solving this?
I guess my position in the grid. If I know I'm at cell ij, that seems to tell me everything I need to know to make the next decision and figure out the cost from there, right?
Exactly. Your position ij defines the subproblem. The most useful subproblem to track for DP in this case is the minimum path sum required to reach cell I, starting from the origin 0, 0. Let's call that value dpi. That value dpij holds the answer to the subproblem ending at cell ij.
Okay, so the state is my coordinates, ij, and the value stored for that state is the minimum cost to actually get to that cell. And the DP table, what does that look like?
Since the state is defined by two variables, I row and j column, the DP table will naturally be a 2D array, basically mirroring the grid's dimensions. Let's say nxm. Each cell ij in this DP table will store the value dpij, that minimum path sum, from 0, 0 to ij. Visualizing this table helps you see which subproblems you need to solve and store.
That makes sense. The table is just where we'll write down the answers to all the minimum costs to reach this cell questions. Okay. All right. Step 2, optimal substructure and state transition. How do we connect the dots between these states? How do we find the relationship?
This is where the optimal substructure idea comes in, and it's usually the core insight. To find the minimum path sum to reach cell ij, think about the very last step taken to arrive there. Where must you have come from?
Well, given the rules only down or right, I must have arrived from either the cell directly above it, I1j, or the cell directly to its left, IJ1. Those are the only two possibilities.
Precisely. So if you want the minimum path sum to ij, it must be built upon the minimum path sum to one of those two preceding cells. Specifically, it's the minimum of the path sum to I1j and the path sum to ij1, plus, of course, the cost of the current cell ij itself, greedy j. The optimal path to ij must pass through either I1j or ij1 optimally.
And that gives us the core relationship, the transition equation.
It does. The state transition equation for this problem is d pi I, j equals mine to d pi 1, j d pi 1, plus greedy j. This equation is absolutely key because it tells you exactly how to compute the solution for state I. Using the solutions you've already found for the dependent states, I1, j and I, j-1. It's the recipe for building up the solution.
Okay, so we know how to get from previous states to the current state, but where do we start? We need a beginning. Step 3, boundary conditions and transition order.
Right, you need base cases or boundary conditions, places in the grid where the general rule might not apply or simplifies. Think about the edges. For the minimum path sum, consider the cells in the very first row. How can you reach dp0, j?
Well, you can only move right, so you must have come from dp0, j1.
So dp0, j pi 0, 0, j-1 plus grid 0. Similarly, for cells in the first column, you can only reach them by moving down from the cell above. So d pi 0, d pi 1, 0 plus greed 0, 0. These form your boundary conditions. Their minimum path sums are determined simply by accumulating costs along that single edge from the start, 0, 0, where dp0, 0 is just grid 0, 0.
Got it. The edges of the grid are the simpler starting cases.
Yes. And just as crucial is the transition order. When you're calculating dpi, j, using our equation, you must ensure that the values it depends on, namely d pi 1, j, and d pi j1, have already been computed. How should we fill the DP table to guarantee this?
If I'm calculating ij, I need the cell above it, I1j, and the cell to its left, ij1. So if I fill the table row by row, starting from the top row, and within each row, I go column by column from left to right. By the time I get to ij, I will have already calculated everything in the row above it, which includes I1j, and everything to the left in the current row, which includes ij1. That seems to work.
Exactly. Traversing row by row, column by column is a valid transition order because it respects these dependencies perfectly. You start with the base case dp0, then fill the first row using its boundary condition, fill the first column using its boundary condition, and then iterate through the rest of the grid, say, with nested loops applying the main transition equation. By the time you need dpi1, j, and dpi-j1, they're already computed and sitting there in your table.
That structured bottom-up fill feels very systematic, very predictable.
It is. And these three steps, understanding the decisions, state, and table, deriving the state transition equation, and setting the boundary conditions and determining the correct transition order, are really the core of formulating a dynamic programming solution.
Okay, so once you have that formulation, how do you actually implement it in code? The source walks through the evolution from a naive approach to something much more efficient, right?
Right. The most direct translation of that recursive relationship we found, dpi, j-adog, my pi 1, j-aj, dpi, j1, plus greedy j, is often just a recursive function. You could write a function, say solve ij, that returns the minimum path sum from the start, 0, 0 to ij. Inside, it would recursively call min, solve I1j, solve ij1, and add greedy. You'd need base cases for 0, 0, 0, and maybe returning infinity if you go out of bounds.
But this is where things get messy, isn't it? This is where we see those overlapping subproblems really bite us.
Precisely. As the source illustrates with a recursive tree diagram, calculating solve IEJ might require solve I1J1, but then calculating solve I1J might also need solve I1J and solve I1J1. And calculating solve IJ1 also needs solve I1J1 and solve IJ2. Notice solve I1J1 is needed by both branches leading to solve IJ. You end up recalculating the minimum path sum to the same intermediate cells many, many, many times.
It sounds like, yeah, a massive waste of computation. Exponential, probably.
It is. The time complexity explodes, growing exponentially, roughly like 0.2 meters plus n in the worst case, because you essentially re-explore vast sections of the possible grid paths repeatedly. This is the brute force recursive approach, and it's almost never practical for problems of any significant size.
Okay, so the first big optimization step is to just stop recalculating things you've already figured out.
Exactly. Method 2 is memoization. It's such a simple but powerful idea. You keep that same recursive structure, but you add a cache or a memo, often just an array mirroring the DP cable dimensions initialized to some sentinel value like -1. Before you compute solve, INECOJ, you check your memo table at IOJ. If it's not the sentinel value, it means you've already computed it, so you just return the stored value instantly. If it is the sentinel value, then you compute it recursively as before, but crucially, before you return the result, you store it in memoish.
Ah, so the insight is the inefficiency comes from asking the same question over and over. If you just remember the answer the first time you figure it out, you avoid all that redundant work.
That's the core DP idea right there. If a subproblem's solution is only needed for its final value, not the specific path taken to get that value, you can cache that value and reuse it whenever it's needed again. This prunes the recursive tree dramatically. Each unique state ij gets computed only once.
And that must bring the time complexity way down.
Absolutely. The time complexity drops significantly down to O(n)m, which is basically proportional to the number of unique states, cells in the grid. You visit each state essentially once. The space complexity is also O(n) because you need that memoization table to store the results. It's a huge improvement over the brute force exponential time.
Okay, so that's memoization top-down with caching. Method 3 is what we often think of as classic dynamic programming, the iterative bottom-up approach, using the DP table explicitly.
Yeah, this is the direct implementation of the systematic fill we talked about earlier. You explicitly create the n times m DP table. You initialize the boundary conditions, the first row and first column, based on the rules we discussed. Then you use nested loops, typically iterating row by row, column by column, respecting the transition order, and you apply that state transition equation, dpi, j equals mine, dpi1, jp-1, plus greedy j for all the inner cells. You just fill the table systematically, building up the solutions for larger subproblems from the solutions of smaller ones that you've already computed and stored right there in the table.
This approach feels very deterministic and controlled compared to the recursive ones. No hidden recursion stack or anything.
It is. It directly implements that valid transition order we figured out. It has the same time complexity as memoized search, because again, you essentially visit and compute the value for each cell in the grid once. The space complexity is also for the explicit DP table. Many people find this iterative approach easier to reason about once the state transition is clear, and it completely avoids any potential issues with deep recursion stacks.
Right. And finally, the source touches on space optimization. Can we get that space complexity down even further? Because sometimes those grids can be huge.
For problems like this one, yes, we often can. Look closely at the state transition equation. dpi j I mod dpi1 j dpi jdm1 plus greedy j. To compute the value for a cell ij, what information do you actually need? You only need the value from the cell directly above it, I1j, and the cell directly to its left, ij1. You don't actually need the values from I2j or ij2 or anything further back, right?
Ah, okay. So once I finish calculating, say, row I don't really need the values from row I2 anymore to calculate row I plus 1. I only need row I's values.
Exactly. Or even better, to calculate the cell I, j within row I, you only need the result from I1, j, which was calculated in the previous row's pass, and the result from I, j1, which is just calculated in the current row's pass.
So wait, could I maybe get away with just using a single row's worth of storage, like a 1D array?
You absolutely can. This is a common optimization. You can use a 1D array, let's call it dprow, of size m, the number of columns. As you iterate through the grid, say row by row, I from 0 to n1, this dprow array will effectively store the minimum path sums for the previous row, I1. When you calculate the values for the current row I, you update this dprow array in place. When you're calculating for column j, the value dprow j currently holds a result from I1j. The value dprow j1 holds the result you just calculated for ij1. You use these two values, dprow j from the previous row, dprow j1 from the current row, to compute the new value for ij, and then you overwrite dprow with this new result.
Whoa, okay, so the single array is cleverly storing the value from the cell above, index j, before it gets overwritten, and the value from the cell to the left at index j1, which was just updated. You have to be careful with the order, I guess.
Exactly. You have to handle the first column slightly differently since it only depends on the value above, the old dprow 0. But for j0'd, dprow j represents the above value, and dprow j1 represents the left value needed for the min calculation. Then you update dprow j.
That's a really neat trick. It drastically reduces the memory footprint, doesn't it?
It does. This space optimization brings the space complexity down to just the width of the grid, or O(n) day if you optimize based on columns instead, all while maintaining the same time complexity. It's a powerful example of how really understanding the dependencies in the state transition allows you to optimize space usage significantly.
Okay, wow. So we've covered quite a bit there, how to get a hint that a problem might be DP, walk through those structured steps using the minimum path sum example, and seen how different implementations tackle the efficiency challenge, from, the slow brute force all the way to that optimized iterative approach. What's the big takeaway here for someone listening, maybe encountering a new tricky problem? How does this help them?
Well, I think the core idea is that dynamic programming provides this really rigorous framework for problems that have that underlying decision structure and dependency between subproblems. By breaking the problem down into smaller, manageable subproblems, the states, figuring out precisely how to build a solution for a state from previously solved states, that's the transition equation, and then solving them systematically in the right order. You can transform a problem that seems overwhelmingly complex, maybe even exponential, when viewed holistically, into a structured, often polynomial time solvable process. It's really about shifting your perspective to see the problem's internal structure and dependencies.
It's like being given a complex machine and learning to identify the key components and how they connect, rather than just being intimidated by the whole thing working together. Less magic, more engineering.
Exactly. That's a great analogy. We've taken a pretty deep dive today into the practical process of dynamic programming, using the minimum path sum problem as our consistent guide throughout. We saw how identifying that decision tree structure and maybe an optimization goal points you towards DP. We saw how the steps of defining the state, finding the transition, handling boundaries, and choosing an order provide the blueprint. And then we saw how techniques like memoization and iterative DP efficiently build the solution, with space optimization sometimes offering that final refinement.
It's definitely a lot of pieces, but hopefully seeing how they fit together step by step through that concrete grid example helps solidify the framework in your mind. The goal really was to provide a clear path through this often intimidating topic, making it understandable and hopefully applicable.
And this, I think, raises an important question for you, the listener, to take away. As you look at problems around you, Maybe there are coding challenges, maybe project planning, maybe even other complex decision-making tasks. Can you start to spot those underlying decision trees? Can you see situations where intermediate results or calculations might be reused, hinting at those overlapping subproblems? Shifting your mindset to look for these patterns is often the very first step towards unlocking the power of dynamic programming in your own problem-solving toolkit.
Something to definitely mull over as you encounter your next complex challenge, a new lens to view problems through.